Hello, good evening everyone. Am I audible?
नमस्कार मैम।
Yes, ma'am.
Audible?
Yes, ma'am, you're audible, ma'am.
Okay, thank you. So today's session is based on week 6 theory. And I think for a graded assignment of week 6, does the deadline still on Wednesday or it changed?
Wednesday. Or
Ma'am, it's Wednesday, ma'am.
17.
Okay, so I think there will be session tomorrow also. I mean, for
Yes, ma'am. Tomorrow is
practice.
there.
Yeah.
Hello?
Yes.
It was quite so. I think is there any signal problem in this?
Yeah. Actually, we'll start our class from, let's say, 8:15 because there are less number of people joining.
Okay.
Ma'am, in the meantime, can we discuss week 5 graded assignment questions, ma'am? Or
Yeah,
should we
okay.
wait, ma'am?
Just give me a second. There is an issue with YouTube links.
Sure, ma'am, sure.
Okay, so which question do you have?
Ma'am, question number 5 and option number 2, and in question number 10, option number 3. I've got 2 doubts, ma'am.
Question number, sorry, please, can you please repeat?
Ma'am, question number 5, and particularly the option number 2 in question 5,
Okay.
and in question number 10, option number 3.
So question number 5 is this fx is equals to 1 minus x to the power 1 by 2, this one.
Yes, ma'am.
So then here you have to find the domain of composite function. So in the previous session, I told that for finding the domain of composite function, you have to work. You have to do it in 2 steps. First, you have to find the domain of innermost function, and then you have to remove all those points from the domain of f, for which f of x does not belong to domain of g, right? So what's your doubt in second option is not coming right?
Yes, ma'am. I'm not able to get the second option, ma'am. I could
Okay,
get
okay. Actually,
fourth
it's
option.
yeah. So you can get fourth option, but second option is written in slightly different way. That's the issue. So here this option says this one. Minus of infinity power 1 shows this and then intersection of minus 2 to infinity. The deadline is over for week 5, right?
Yeah, ma'am. It was yesterday, ma'am.
Yeah. So see here it's written in a bit complicated way. So what you can do, first you will draw a number line and plot these 2 sets there. Okay. So these sets are suppose this is my minus 2, minus 0, and 1 is this. Okay. So then this set, this minus infinity to 1 will contain this number line, right? With the closed bracket. So this is your minus infinity comma closed. Now minus 2 to infinity will contain this bracket, right? This line. This line will shows us minus 2 to infinity. Now what we have to do, we have to take the intersection of these 2 sets. Right. So for intersection of these 2 sets means the points which are common in both of the sets. So from the number line, you somehow guess that this portion is common in both of the sets. Right. So that means this minus infinity to 1 closed intersection with minus 2 to infinity. This set is nothing but this closed line segment, minus 2 to 1. Right. And then what we have to do, we have to take a union of this line segment to this segment, minus 2 to minus infinity to minus 2. And both of them are open. So this interval is actually this line segment, right? Minus infinity to minus. Now what you have to do, we have to take the union. So that means we have to attach these 2 line segment together. So if we attach these 2 line segment together, what we will get? We will get this line segment, minus infinity to 1 close to 4. Right. And there's a mistake. Minus infinity to 1 we did, and then from minus 2 to infinity to we did, and we take intersection. So if we take intersection, it will be minus 2 to 1. That's correct. And we have to take union with minus infinity to 1. So the line segment is coming out to be this set. If we solve these, if we solve this intervals, then it turns out that it's nothing but minus infinity to 1, right? And this is same as the whole real number subtracted from 1 to 2, right? Because if you think about a real line, so this is real line, this is 1, right? So in the real line, if we remove this portion, then what you will left, we'll left with this line segment. And this line segment is same as minus infinity to 1, right? So that's why here both the second option and the fourth option is same. It's written in a slightly different way, but they are same. Now it's clear?
Yeah, ma'am. Ma'am, it was quite tricky, ma'am.
Right. So you have to go step by step. First, if you do with the line segment, then it's I think it's easy. Not easy, but yeah. you can understand. First, draw the line segment for this interval, then draw the line segment for this interval. Then observe what is the common portion between, right? So here it's clear that this line segment contains this part, this line segment contains this part. So obviously this is the only common portion there, right? And after that you have to do union. So in union, intersection is observative, but in union what you have to do, you just have to paste these two line segment over each other, right? So if you do that, you will get your answer minus infinity to 1, then which is seen as real number minus 1 2. Okay. It will be more handy when you do some practice. Okay.
Yeah, ma'am.
So
Thank you, ma'am.
this question was done.
Ma'am, question number 10, option number 3.
Option number 3. So the amount she is supposed to pay after applying D2 only is approximately. So is this answer is not true, or what's your doubt?
Actually, the option, the answer they have given does not include that option, but I think it should be there. That's what the confusion is.
Okay, so for that we have to solve your question, the whole question. Okay, so I'll get back to this question at the end.
Sure, ma'am. Not an issue, ma'am. Thank you, ma'am.
So let's start our week. Question number 10, option number 3.
Activity 5.
This was summary lecture. No?
Ma'am, are we not doing
This is
summary?
summary. Yeah, we are dealing with summary. Before
Revision
starting
about
the
the
session, he just has.
Okay, ma'am.
So now let's start the session. So this session is dedicated to week 6 theory, particularly. So in week 6, we discuss a very useful function called to be logarithmic function. Okay, so I'll start with I'll share the PDF at the end. So let me give some motivation that how does log come into picture. Okay, so you guys are familiar with the exponential function, right? Okay, so exponential function, that means f of x is equals to a to the power x, right? And in this function, we have some restriction over over the base. Here a is the base, and over the base we have some restriction. First thing is that my base should be, this a should be strictly greater than 0. That means positive, because obviously if you take any negative number and you do its power, which is of the rational form, that means minus 1 to the power 1 by 2, right? So this root of minus 1 is not defined. It's not a real number. So that's why we restrict ourselves to take a to be a positive, right? And another thing is we try to restrict ourselves that a is not equals to 1. But if we take a is equals to 1, then also this function f of x is just a constant, right? So if you remove these two cases from a, then what we obtain, we get that f of x is equals to a to the power x. This function is actually 1 1 and onto. It's not onto although, but if we restrict our image set, then it will be onto, because 1 1 is clear to everyone, right? This function f of x is equals to a to the power x is a 1 1 function. Why it's 1 1 function? Because if you take x1 is equals to x2, then it is obviously the thing that a of x1 is equals to a of x2, right? So that means if you take or we can say in different way that if we take distinct inputs, then the output will also be distinct. There is a 1 1 correspondence between each x and each ax. That's the definition of 1 1 we already know, right? So that means this function, this exponential function, is actually a 1 1 function. And how does the graph of exponential function look? So if you remember, we divide our graph into two cases, when a is between 0 to 1 and when our a is strictly greater than. In this case, the graph looked like this thing, this decreasing type of wave. And when we have a to be strictly greater than 1, we get this kind of graph, right? So observing by looking at the graph only, we can say that it's a 1 1 function because it satisfies the horizontal line test, right? Horizontal line. That's the another explanation for being this function a one-one function. Now, what happened if we restrict our domain towards this section, this positive y-axis section? Then what we'll get? We'll get that every point on this y-axis, we have a unique pre-image. That means every y here belong to a unique x here, right? So that means if I restrict my function f towards the domain, I'll take the whole real number, and the codomain, I'll take close interval or open interval 0 to infinity. That is positive y-axis, right? So if I do this thing, then what I'll get my function f is 1, 1 as well as on 2, right? So that means if we restrict our exponential function f of x is equals to e to the power x over this codomain and using this domain, then what we get? My function is 1, 1 as well as on 2. Is there any doubt in this fact that how
Ma'am,
we
can you
come?
just explain once more how it is 1, 1 and onto?
Yeah. So by looking the graph of exponential function, you can easily check that it's a 1, 1 function because it satisfies the horizontal line test. What does horizontal line test says? That if you draw a horizontal line parallel to x-axis, and if it cuts the graph exactly once, then it's a 1, 1. So here it is satisfying the condition because it will cut the graph exactly at 1, right? So using the horizontal line test, we can easily say that it's a 1, 1 function. Now, if we restrict our codomain towards this section, this positive y-axis, right? So if we restrict our codomain towards positive y-axis, then we get that every y, there is a unique x. Such a way that y is equals to a to the power x. Because again, by observing the graph, you can see. Because this, if suppose this is the graph, and if you take this y, then just draw the line, you will get some point and you will take perpendicular x, right? So for every x, we have a particular, for every y, we have a unique x in such a way that a to the power x is equals to 1. And that's the thing we need for saying that onto, right? So function is onto. So that's why exponential function restricted to this codomain is an onto function. So that means our exponential function will behave like a bijective function, right? So what does it mean? So that means a to the power x is a bijective function. Bijective function means a function which is 1, 1 as well as onto. 1, 1 plus onto means bijective, right? And we know that if a function is bijective, then there exists an inverse for that function. Then there exists the inverse, because inverse will always be unique. So the inverse for our function a to the power x, right? Because you guys, I think you guys are already familiar that if we have a function f, if f is bijective, that means 1, 1 plus onto, then there exists, this is symbol for there exists, untai. So then there exists the unique function named to be the inverse of f, denoted by f inverse, in such a way that if you composite these two functions, that f composite f inverse, this should be same as f inverse composite f, and this should be same as identity function. Identity function means f of x is equals to x function, right? So whenever we have a bijective function, no, if a function is only injective, then it need not to be have a inverse. For inverse, we need bisective. I mean, we need on. Then only you can reverse it, right? Because if you don't have onto, then when we take f inverse, let me explain. See. Okay. Stop. About bisective. Okay. So suppose f is a function from a to b, right? And f is 1, 1 as well as on. Then what happened? Then there exists the unique function f inverse. Now f inverse will be a function from b to a. F inverse will be a function from B to A, not A to B. In such a way that if you compose these two functions together, that F inverse composition F, this should be same as F composition F inverse, and this should be same as the identity function. If this happen, yeah. If I mean, this will happen only when your function is 1 as well as on. Then only we can say that a function is bijective function and there exists the inverse of that. So same case is happening here. When we take our exponential function f of x is equals to a to the power x, with respect to these two restrictions, that a is not equals to 1 and a is strictly greater than 0, then we get that f is a 1 function. And if we restrict our codomain to be 0 to infinity, then we will get f is also an onto function. So that means f is a bijective function. So that means there should exist one inverse of that f, right? So that means we get an information, okay, my exponential function is a bijective function. So there should exist some function f inverse. In such a way, it should satisfy these two conditions. F inverse composition with f is equals to f composite with f inverse is equals to identity, right? So this f inverse function is named to be the logarithm. Right. That means we develop a function, logarithmic function, which satisfy all the inverse property of exponential. So that's how we define the logarithmic function. So let me give you the standard definition first. So you guys, you guys get the motivation why we want to define a function, right? We want a function which will possess all the inverse properties of our exponential function. If we restrict our codomain to be 0 to infinity, and that function is known to be the logarithmic function. Okay. So the logarithmic function is defined as, so we say that y is equals to log base ax if and only if x is equals to a to the power 1, right? So that means this function that f of x is equals to log base ax, right? So it will give us f of x is equals to y if and only if a to the power x, a to the power y is equals to x, right? So it's some sort of a reverse kind of, right? Because here what we are getting, if we take input to be my x in this logarithmic function, if my input is x, then what will be the output? Output will be y. And in exponential function, what is happening? Here input is y and output is x, right? So that means here the role of input and output are getting the reverse of each other. So that's how we define the logarithmic function. Yeah. So that's why we need, we want it to be bijective. If we take the range set, if we take the codomain set to be the whole real number, then it won't be bijective. I want it to be possess a bijective nature. That's why I take the codomain to be 0 to infinity. Okay. So in this fashion, we define our logarithmic function. So logarithmic function says that y is equals to log base ax if and only if x is equals to a to the power 1. Is there any doubt in this definition? How does logarithmic function define?
Can you give a small example like of this so that we can get the idea?
Okay. See, if you take your a to be 2, then what do we need? What do we know? That 2 to the power 4 is 60, right? So that means here what I did in exponential function 2 to the power x, this is my exponential function, right? So here I take input to be 4, and what I'll get output to be 60. Now logarithmic function will be that function, log base 2 of x will be that function which will use the inverse of which will work as an inverse of 2 to the power x. That means if I consider f of x to be log base 2 of x, and if I take my input to be 16, then the output should be equals to 4. So that function is known to be the log base 2 of x. I mean, what I want to say that the logarithmic function is nothing but a function which will give us the inverse of our exponential. That function is known to be the logarithmic function, and it defined by a simple line. We simply say that y is equals to log base ax if and only if a to the power y is equals to x. You should remember this line first. Understand this line, that if this happen, I mean, if this condition happen, y a to the power y is equals to x, then this will happen. That y is equals to log base x. And I mean, vice versa is also true. If this happen, then this happen. This if and only if means this direction is also true and this direction is also. That's the thing. Now here, over the base, we have some restriction. First thing is that a is greater than 0, a is not equals to. Right? Same restriction we will follow with the logarithmic function also. Here your base should be strictly greater than 0 and a should not equals to. Since they are inverse of each other, that's why they respect the both conditions which we already taken for defining the exponential function. Okay. So we know that if f is a function from a to b, then f inverse will be a function from b to a. Right? I mean the role of domain and range will be right. Logarithmic function is actually defined using the exponential. And when we define our logarithmic function fully, we can say that these two functions are inverse of each. So log is actually some sort of inverse of exponential function. Some sort of what? It's exactly the inverse of exponential function only. Okay. So we know that if f is a function from a to b, yes.
Like if you
Hello?
are having an exponential function, so its inverse will be its logarithmic, right? Logarithmic.
Right.
Yeah,
That's
got
the
it, got
thing.
it. Thank you.
I mean, this is the main, what you can say, origin of logarithmic function. This is the only idea behind the picture, that why we want logarithmic function. Because log is some sort of strange thing you ever see, right? Other exponential function is quite natural because we want to take powers of numbers, right? But logarithmic function is a little bit strange. It's strange because it's actually defined for giving us inverse of a particular function named to be the exponential function. Okay. I think I don't know totally how many formulas, but yeah, there are a pretty much formulas. Now let's move toward the codomain analysis. So this fact is clear to everyone that if we have f is a function from a to b, where a I'm taking the domain and b is the range. I'm not taking codomain, I'm taking range. Okay. And f inverse is although if we take in bijective function, then range and codomain both sets are same, right? So if f is a function from a to b and f inverse is a function from b, then f inverse will be the function from b to a. That means the role of codomain and range will get changed with each other, right? So in exponential function, what happened? If we take exponential function f of x is equals to a to the power x, then we know that it's a function from real number to open interval 0 to infinity. So that means if you take the logarithmic function f inverse of x to be the log base ax, then this f inverse will be a function from open interval 0 to infinity, 0 infinity to real. So that means the domain of logarithmic function will be open interval 0 to infinity. This is a very important fact you should always remember. Okay. So many people get confused about the domain of a logarithmic function. That logarithmic function has domain open interval 0 to infinity, not whole real line, and has the range whole real line. Okay.
Ma'am,
Yes.
ma'am, how is the function bijective if the codomain is not equal to the range?
No, if codomain is not equal to range, then the function won't be bijective. But here I'm defining my exponential function in such a way that I'm taking the range to be the codomain. That's why it will become bijective. I mean, what I did, I'll consider the nicest nice behavior of exponential function, right? I mean, I won't take the negative y-axis because I want that to be bisected. That's why the domain of logarithmic function is coming out to be open interval 0 to infinity. That's the reason. Otherwise, in general, you know that exponential function is not bijective, right? In general, the exponential function is not bijective. But if we restrict our range, if we restrict our codomain to be 0 to infinity, then only it will be bijective.
Okay, got it.
Ma'am, so every log function will have the same range and domain.
Every log function which define in this log base ax. If you compose it with this function with another function, I mean log base a of x minus, this obviously have some different domain and right. But you have to find out the domain of this function by composition of function, right? Composition of function, because it's actually composition of two type of function. So every logarithmic function, if my function f of x is this log base ax, then this function has domain open interval 0 to infinity. And the reason is because we took our exponential function's codomain to be 0 to infinity. Then only it become bisective, and then after that we define logarithm. That's why the domain is 0 to infinity, and the range is the whole real. Okay. Now let's move toward the graph of function and all other properties of logarithmic function. Okay. So again, look for the general case. Again, suppose that if we have a function f from suppose f and f inverse are inverse of each other. Then I'll give you a fact that the graph of f inverse will be just a reflection of graph of f with respect to the line y is equals to x. Right. So that means if you have some function f and you have that function's graph for sake of generality, let's say we have this exponential function. This is our exponential function e to the power x when a is cyclic with it, right? And I restrict my range set here. So if now I have a graph of a function, I want to determine what's the graph of its inverse, right? So what I'll do, I'll draw this line. This line is y is equals to x line, and I'll take the reflection of this graph about this line. I mean, if you place the mirror over this line, so whatever reflection you will get inside the mirror, that will be the graph of f. Okay. No, not y is equals to x. Right. So if we take the reflection of this thing, what will happen? This graph will, right? This is the reflection of this. Let's see using the Desmos. My screen is visible, right? So if I take simply y is equals to let's say 2 to the power x, right? So then this is the red one is the graph, right? And let me zoom. That's now if I draw the line that y is equals to x line, then this is the line. So the inverse of this graph should be the image of give us the reflection of this red graph about this blue line, right? So if I want to draw the y is equals to log base 2 of x, right? So this is the graph of log base 2 of x. See, here you get the clear picture. How does the graph of logarithmic comes? Actually, what we have to do, we have to take the reflection of a to the power x, this graph, over the line y is equals to x. And it's a general way. If you have a function, and you know the graph of that function, and if you want to find out the graph of its inverse, what you have to do is just have to take the reflection of that graph via the line y is equals to x, right? So here we did a case where the value of a is actually strictly greater than 1. So in place of greater than 1, if I took the value, let's say between 0 to 1, then what happened? Then this will be the graph of e to the power x. And here, in place of base, what we have to do? We have to take 0.5, right? So here also you observe that this red one is a graph of your exponential function. And if we reflect this red line, we'll get this graph, this green line, this, right? Because this is a reflection, this green one is a reflection of this red line over the line y is equals to x, right? And if we take this to be our graph, I mean, this is the second part of the graph e to the power x. And if we reflect our this red graph over this blue line, what we will get? We will get this green one, right? So this is the second case when our base is between 0 to 1. Then the graph of log x will look something like this kind of picture. This green. It will be some sort of asymptotic behavior over the y-axis, and then we have a decreasing behavior over the x-axis. Okay. So let me finally define.
Ma'am, I have
So
a small
again,
doubt.
yes.
Ma'am, can you open the Desmos again?
Yes.
Ma'am, like here, written 0.5 log 0.5.
Your voice is.
Am I audible now?
Huh.
Ma'am, as you said that log gives us the exponent. Okay. Here written log of 0.5x. So shouldn't be that x be the answer of log 0.5?
Oh, see, here actually in Desmos, they only accept y is equals to x kind of form. That's why I won't change the behavior. I mean, here then the x's will change. Now that's why I take same y is equals to x.
Can you write the same thing on whiteboard and let me know how that log statement will be?
See. So what we have for log, we have this statement, right? That y is equals to log base ax if and only if a to the power y is equals to x. Right. So here, if I take my a to be 0.5, then the function will be, this function will be 0.5 to the power y. I mean, x is equals to 0. Here, their Desmos only accept y is equals to x format. That's why I write it down. But the log will be this kind of thing, that y is equals to log of 0.5 of x. Now it's clear?
Yes, it is clear. Thank you.
So let's move toward the graph of logarithmic function. So when our base is between 0 to 1, the graph will look a little bit different. And when a is strictly greater than 1, it's a very easy, we understand, right, how actually it comes out to be this graph. And it's intersect at the point 1 over the x-axis. Okay. This is your y-axis. And when my base is between, I mean, the value of a is between 0 to 1, then the graph of logarithmic will be this type of base.
Could you just show the 0.5 thing once more?
Not sure.
No, the ones that you wrote on the whiteboard.
Oh, yeah. See, actually, he got confused between y and x. So in Desmos, what happened? We have to take y is equals to x expression. Then otherwise,
y is equal to log base 0.5 raised to x, right?
X.
Oh.
These two expressions are actually same. I mean, if you put input, I mean, if you consider input output thing, then it will give us the y-intercept.
Okay.
So this is a graph of the graph of logarithmic function. So in this case, we get that logarithmic function will be some sort of decreasing function, and in this case, it will be an increasing function. Now, via observing the graph, just answer a very, I mean, you guys are now, I think, familiar with limit concept. So if limit of x goes to infinity, log base ax, what will be the answer in this case and in this case. What will be the answer?
Will go to infinity only.
Minus
In
infinity.
first case.
In first case, minus
infinity.
Minus infinity, right?
It is minus
Because
infinity.
as we move towards the infinity, the graph is actually going more decreasing kind of pattern will happen. So that's why it will be minus. Now limit x goes to minus infinity. Now here this limit we can't talk about, right? Because our domain is between
There's an
0 to
asymptote between.
yeah, so that's why we have to talk about this x going to 0 limit. So if limit x going to 0, log base ax is actually plus infinity, right? Because it's actually asymptotically growing towards the y-axis. So that's why it will go towards the plus infinity. These two limits are clear. Is there any doubt?
The second part is what you said again. Limit goes to
0 actually, because the domain of logarithmic function does not contain negative
It is
values. That's
got
Yeah, hello, ma'am. Could you please tell once again the limit, the two things, how you can. Now, how did you thought of it?
See, as x goes to infinity, we observe that our graph is actually going more. Yeah, right. I'm right. I got confused. See, what happening here as our x is going to infinity, my graph is actually becoming more decreasing kind of. So that means as x goes to infinity, it will reach out much larger negative values, right? So here it will be minus 10, then here it will be, let's say, minus 15 and so. So that means we are observing that as x going to infinity, the values of y, whatever we are getting, are much larger values in the negative y-axis, right? So that's why we get the intuition that this limit will be minus, right? And as we take our x more closer and closer to 0.0, as the limit x going to minus infinity doesn't make sense here because we don't have outputs over the negative real axis, right? -1, -2. We don't have such kind of values. So that's why we took this limit x going to 0, because we can take we can go much closer and closer to the point 0, 0, right? So as we go near to 0, we observe that our graph is actually kind of behaving asymptotically toward this positive y-axis. So that means if I take this x, so then I'll get, let's say, 10, then I'll get 15 and so on. I mean, it's actually increasing kind of behavior, isn't it? That's why this limit will be plus infinity, right? Similarly, we can observe here that limit x going to infinity, log base ax is actually infinity because it's growing in this direction, positive y-axis direction. And similarly, if I take limit x going to 0, again I am taking 0 because obvious reason, the domain, then the log base ax is actually minus 50, right?
Okay, got it. Thank you.
Yeah, correct. It's strictly increasing and strictly decreasing. Because via the graph, it's quite obvious, right? So these are the two, end behavior observed. And also we observe that it's, in this case, the logarithmic function will be a decreasing function, right? And in this case, it will be an increasing function. Okay. So now let's move toward the properties.
Ma'am,
Now,
limit is not
Ma'am,
this
I
limit
have a
concept.
question, ma'am.
Ma'am, this limit concept is
yes.
not there in week 6, ma'am.
This limit is not in week 6. Okay, but via the graph you can observe, right? I mean, you guys are now familiar with the end behavior of polynomial and all things, so it's better
Yes,
to observe. Right.
Ma'am, I am asking like if logarithmic function is a decreasing function, that means exponential function will be increasing.
Right. So in this case, no. I mean, when a is between 0 to 1, 0 is less than a is less than 1, or exponential function is also a sort of decreasing. It's not the case. I mean, you can't say that if f is decreasing, then its inverse is also, then its inverse is increasing. That's actually not happening here. See, in this case, our exponential function look like this, right? It's also
Yes,
a decreasing function. And in this case, its inverse is actually is also a decreasing.
Okay.
So it's not a general case that if f is increasing, its inverse is decreasing. Okay. Now, see, all these things are conceptual, right? From here, you will get the idea that why log is defined, how log is defined, why log is not defined over the negative real axis, right? Why only it's defined only over the positive real axis, right? So these are sort of questions you should remember. I mean, you should first understand that why things are happening and then keep those things in mind. Okay. So using these things, we derive some of the algebraic properties of logarithmic. So let me state them. The laws of logarithm. This conceptual part is clear, right? Is there any other doubt for graph and all? No, right?
No, ma'am.
No.
So laws of logarithm. So all the laws of logarithm you can easily prove via this identity that y is equals to log base ax if and only if a to the power y is equals to x. Okay. So this identity you always have, you should keep in mind. Okay. So the first thing is that one note I'll make that log base ax is well defined. Only when there are restrictions over a and x, right? So over a, we have the restriction that a should be strictly greater than 0, a should not equals to 1. And over x also we have restriction as my domain is, hello? Please mute yourself. So that means whenever you have log base ax, there will be some restrictions over x and as well as there will be restrictions over a. First thing is that a should be strictly greater than 0 and a is not equals to 1. And the next thing is that our x is also strictly greater than 0. This thing is actually very important. X is strictly greater than 0. Okay. So whenever you have to find, whenever some question asks that you have to find the domain of logarithmic of something, then you have to apply this condition that your x should be strictly greater than 0. That will give you the most of the answers of domain questions based on logarithm. For example, if you have to find out the domain of, let's take the simple example. If you have to find out the domain of log base 5 of x minus 1, right? Then what you have to do, you know that this part should be strictly greater than 0. That means your x minus 1 should be strictly greater than 0. That means your x should be strictly greater than 1. So whenever I have x strictly greater than 1, I'll get x minus 1 will be strictly greater than 0. That means this part will be strictly greater than 0 and my log will be well defined. So that means the domain in this case will be what? 1 to infinity. Again, we know that at 0 it is not well defined. So that's why we have a strict inequality. Strictly greater.
Ma'am,
Right? So this
shouldn't
will
we
be the domain
include
of
1?
1 over what?
Ma'am,
No,
including
zero.
1.
No,
No,
it
it's
will be
Log
0
zero
then.
then.
Greater than 1.
0, right?
Strictly
no,
greater
Log
than
zero is not defined.
Okay,
Log
ma'am.
zero is
Okay.
not defined.
Log 0 is not defined. We get this limit now. Limit x going to 0, we have plus infinity kind of, right? That's why it's not defined. Another reason also there, but it's okay.
ma'am, is this one to be included?
No. One should not be included because from the graph and from the all discussion we get that at 0 log is not defined. And also we get this limit, right? Limit x going to infinity log base x is equals to plus infinity. Right. And also, yeah.
Okay.
At 0 log is not well defined. You should have this strict inequality. Okay. So let's move toward the very simple properties. First one is, I think you guys are already familiar, log base a of mn. And I am assuming then mn and a all are satisfying the given restrictions for defining them. So log base a n plus log base a. Okay. So now, if you want to prove this property of log, what you have to do, you have to keep in mind this thing, that y is equals to log base ax if and only if a to the power y is equals to x, right? And you are familiar with the arithmetic over the powers, right? I mean, you guys know that a to the power r and s is r plus s is equals to a to the power r into a to the power s. So we'll use all those things to prove this inequality, right? So what we will do? So let's take so say a1. So let's say capital A is equals to log base a of m. Okay. From here, what you will get if you apply this inequalities, what I'll get, I have to take a to the power this number, then it will be equals to x. So that means I have to take a to the power this number, then it will be equals to m. So that means mn is equals to a to the power capital. This fact is clear to everyone. Is there any doubt how we obtained this equality? Just use this equality that a to the power y is equals to x. So that means a to the power capital A is equals to m, right? Similarly, if I consider b is equals to log base a of m, then this will imply that a to the power b is equals to m, right? So to the power capital B is equals to m. And similarly, if I take c to be log base a of n, then I get a to the power c is equals to. So that means, what does it mean? So it means that mn is actually equals to a to the power, which is actually equals to a to the power b and into with a to the power c. So that means a to the power capital A is actually a to the power b plus, right? Here we use the power exponential power. That if we have product, then the power will get added. Right. So now if you do again the reverse kind of thing, we will simply get that this a is equals to b plus. A is equals to b plus c. If you compare the power also, then also will. So that means what I'll get the required equality, whatever. That log base a, because the value of a is this, is equals to log base a m plus log base a, right? So this is a central idea for proving all the properties of log. You can use a little bit of right. So that means all the properties you can easily prove via this inequality, and there will be some algebraic multiplications, algebraic computation. So I'll just state all the properties only. So first thing is this, the second one is log base a of n by n. It's actually equals to log base c of n, and this log base c of n. The other one is log base c of 1 by n, and this is minus of log base c. This power rule is also important, that log base c of n to the power r is actually r log base a of. So these are the properties we require. So using these properties, you can solve questions. Right. Now there is one very important property about log, which is called the change of base. What does it say? So it says that if you have this thing, that log base a of x, then you can change our a into any other base using this property, that log base b of x upon log base b. Again, I am assuming that my x, a, b, and c are satisfying all the restrictions, whatever it is. Yeah. So this is the derivative resolution. Is there any doubt in this thing? It's quite easy, right? We just have to use the property.
Can you explain change of base a little?
Yeah, sure. See, change of base rule says that if you have all the candidates satisfying your condition, that means x should be greater than 0. Again, a and b should be strictly greater than 0, not equals to 1, all kind of. Then if you want to change your base of logarithm to be some other base, then you can use this equality, that log base a of x is actually equals to log base b of x upon log base b of x. Right. Again, you can prove this thing via the same thing. You have to convert into exponential and then use the rules for exponential and then solve it. Okay. It's not that difficult, but you should remember it first thing, that using this change of base, what we will do, we will, we will talk about only two logs. First log is which has base 10, and the second one which has base the e, the exponential number, right? So because of this property says that log base a of x is equals to log base b of x upon log base b of x. Is this clear? It's actually a formula type.
Yes.
Yes, it is clear. Thank you.
Okay. So because of this property, we observe that a actually, it's not important to take. You can talk about only two type of logarithm. That first logarithm is log base 10, and the second logarithm is log base e, which is known as to be ln, the natural logarithm. Natural. Right. So because of these this base property, we can say that okay, we don't have to consider all the logarithms. Because obviously, if you want to define logarithm, first you will fix your base and then you will talk about the function, right? So it's enough to take these two things. Why we take these two things? Because this 10 is pretty much easier to handle, and this logarithm actually this come into picture in very, so many examples are there which
And log e is equal
applications.
to, that is ln.
Log base e, whatever base e is there, then that log is written to be ln. You have seen somewhere that there is written to be ln. So, but ln is actually denoting that log base is e, right? So in this course, sometimes they already explicitly says that it's a logarithm. It's a logarithm base is e or 10. But in general, ln is actually referred to the logarithm with the base e, right?
Ma'am, it
So
is
that's
log
the reason.
log e base 10.
Here the base is 10. This log is actually generally taken to be the log, and that log is said to be. If we have log base 10, then in common we just use log, right? This is log. But if you take base e, then this log is actually written to be ln. That's a notation, right?
Okay.
Frequently used notation. Because in this case, you don't have to write base 10 and e, right? So many times. You can simply say that's a log and it's ln.
And when do we use this log e? Means
See,
log.
in so many applications it occurs. In engineering, there are so many cases where this log base e come into picture. That's why we consider it to be an.
Okay.
Ma'am, can we say that for like if we keep x as any integer other than 1, because at 1 it will give log 1 is 0, it will give a irrational number because the graph only has one root at 1. So if we keep any other integer, would it give a irrational number all the time?
Hello, ma'am.
Hello, am I audible?
Yes, ma'am. Now
Yes,
you're
ma'am.
out.
Yes, ma'am.
Yes.
Okay, so now there are not that much things.
Ma'am,
I
your
think for
screen is
theory
not
part,
visible.
yeah. Actually, charge. So I think if you consider, then this. Okay, we have one more property. So the last property is this property that if you take a to the power log base a of x, then it's actually equals to 1. It's a very famous property. Not 1, x. Right. So that means if you take a to the power log base a of x, then it's actually equals to x. Why is this so? Because again, if you consider this thing that y is equals to log base of x, if and only if a to the power is equals to x, then in this case, if you observe, then if you take this to be your y, then what will happen? That log base a of x is equals to y, and y is what? So y is log base x. That's why this equality makes sense, right? This is another
FO
property.
F inverse.
Right, correct. FO F inverse is equals to identity function. We need the power log base x and another property. I think these are the only things we see in week 6. But actually, it's I mean, the theory is not that much difficult, but you have to do some practice. Then only.
Yes, ma'am. Questions are on another level only. Theory is on another level.
Yeah, theory is this much only. Because questions, whenever
Ma'am,
there
even
are
the-
some properties, that
Even
will
the
be.
activity level of questions are so high that.
Yes, ma'am.
Okay, so what we can do now, I don't have that much question to do. I mean, I have very simple question. In these questions, you can easily do.
Ma'am, could you do
So
the
what we
activity
can
question
do?
itself?
Ma'am, can you take doubts from
Right.
activity questions?
Yeah, so we'll start doubts from it. We have an hour. So let's see. So I'll yes.
Yeah, how do you put base ma'am in Desmos? Log to the base 3. I didn't get that.
Base what?
No,
You
while
just
drawing
write
the
log,
graph in Desmos, how do you put the base values?
See,
There is only
for
power
this
value.
underscore, you have to use underscore.
Shift
For
or
this
shift
thing,
plus underscore, ma'am?
No, only underscore.
Okay, thank you.
Underscore. Whenever you have to write in something in base or in the lower case, then you will use underscore.
Okay.
Okay, so let's go via activity 6.1. Is there any doubt in 6.1?
Ma'am, I just suggest you start from the start. So, like, whoever has doubts will get it cleared and we can progress throughout.
Ma'am, question number 4, ma'am.
Sorry, what you want to say? Question number 4 is there. What you want to say? Just repeat. Please.
No, I was just
Hello?
saying, ma'am, if you could just go question by question, like 1, 2, 3, 4, then I think we progress also like naturally, and then whoever has doubts in between gets cleared on the way.
Yes, ma'am. Actually, that
that's
will
good,
take a
but
lot of time to complete, ma'am.
Right. I
It will
mean,
take a
if
lot of time.
there will be some
You
easy
can just
questions
start
also.
with the practice assignment, like one by one.
Yeah, so ma'am, I think if you the easy
Even
questions
half
will
of
get
them
solved
will
very
like give the
quickly.
idea.
Okay.
Yeah, so
Yes, ma'am.
the
That's
easy
what I'm
questions
saying,
will
ma'am.
get solved. The easy questions will
One,
get solved quickly,
one,
and
two,
then
one, two question, ma'am. Okay, continue.
Okay, so
yeah, sorry.
what we can do? Let's start from activity question. Okay. So activity.
Ma'am, my suggestion was maybe 1, 2 question from activity question, and we can jump to practice assignment only.
Yeah, exactly.
Yeah, we can.
Yes, ma'am.
We will solve practice assignment first. Then
In practice assignment, ma'am, 6.1 question number 4 is good, ma'am. We should try it together.
so what you guys want? Practice assignment first or
Ma'am,
activity?
just go. I
Practice
I would suggest, like, if you go to the practice assignment questions, and even the easy ones will get solved very quickly.
Yes,
The hard
right.
ones would take some time, so that would make it easier, now, because practice assignment is good for everyone, I understand. But then the ones who would have doubts and activity questions would just stay unresolved if they're not touched.
Okay, so let's go via practice assignment. I mean, sorry, activity question. Oh, so, yeah, start with the 6.1. If we left other things, then there will be always, I mean, there's a totally dedicated session for solving your doubts, right? So we can continue there also. So let's start with activity 6.1, question number 4, right?
Okay.
So the set of all x for which there are no function of the form. Yeah, the deadline can't be. So in this question number 4, what you have to find some sort of domain kind of thing you have to find. That it says that the set of all x for which there are no functions of the form f of x is equals to log base of x minus 1, 1x plus 1, x plus 1 square, right? So again, you have to use the restriction, whatever we discussed for defining the log. Okay. So the function is actually given here. So f of x is equals to log of x minus 1 upon x plus 1. And then here it is x square plus 1 upon x square. And they say that the set of all x for which there are no functions of the form f of x. So that means we have to find the set of all values of x for which such type of function is not defined, right? So here again we saw some log base a x type of thing. So I already told you that for defining log, for defining logarithm, we have some restriction over the a and x, that my a should be strictly greater than 0, a should not equal to 1, and x should be strictly greater than 0. So we'll check all these restrictions over here. So here the base is simply x minus 1 upon x plus 1, right? I want it to be strictly greater than 0, right? Because a should be strictly greater than 0. So that means what I want my x to be strictly greater than, right? Because you can simply see here that if you take x to be anything less than 1, then this minus sign will dominate this number and we lead up with the negative, right? Oh, so this one restriction will get via this thing, a is strictly greater than 1. Now what I want a is not equals to, right? So what I want x minus 1 upon x plus 1 not equals to 1. So what we will do, we'll try to find out those x for which it's equals to 1. So let's say it's equals to 1, because equality is more easier to handle, I mean more easily we can handle in place of inequalities, right? So that what does it mean? So it means that x minus 1 is equals to x plus 1, but here we get x and x cancel out, that means minus 1 is equals to. So that means there does not exist any x for which this thing will, because this thing leads us to a contradiction, right? So that means this is trivially true. Now let's get back to this condition that my x is strictly greater than 0. So here in place of x, what we have x square plus 1 upon x square minus 1. And I want this to be strictly greater than 0. But you can easily observe that x square plus 1, x square minus 1, here this upper, what you can say, numerator part, this part is always positive because it's a square function and two positive things are added. So that means if I want this thing to be positive, what I want, this thing, that x square minus 1, this should be strictly greater than 0, right? So what I want x square minus 1 should be strictly greater than 0. So that means my x square should be strictly greater than 1, right? So what does it mean? So it means the square is strictly greater than 1 when my x lies between, that means we can easily solve this. This means x is strictly greater than 1 and x is strictly less than minus. Because if you take any number which is lesser than minus 1, its square will become positive and it will be greater than. So that's why this inequality here.
All the values which should not be between a1 and minus.
So ultimately what we'll get, that x should be either strictly greater than 1 or it could be strictly less than. That means x should not belongs to this interval minus 1 to close. So that's why the answer is a close interval minus 1. Right. So that means all restriction lead us that x should not belong to minus 1. So this question is clear, right?
Yes, ma'am.
So
Ma'am,
this is fine.
Ma'am, the fourth option should also not come now, ma'am, because it is open closed interval minus infinity comma minus 1. So in that fourth option, minus 1 is also included now, ma'am. Similarly, for closed open 1 comma infinity. So in that case, both minus 1 and plus 1 is included now, ma'am. So it should not come for closed interval 1 now, ma'am, because 1 is included.
Yeah.
So for the
right.
base, it becomes 0 now, ma'am.
It becomes 0, right? So yeah, here this should be correct. That's why fourth option is also, I mean, because of 1 point, it's not true. Although we have to find, I mean, the question says that the set of all x, right? So here this set does not contain all x. So I think that's why it's this option is not. Although it
Okay,
contains
ma'am.
minus 1 and 1, but the question says we have to find the set of all x. So
Okay,
because
ma'am.
of this reason, I think this option is.
Okay, ma'am.
Okay.
So,
So
ma'am,
now let's
ma'am, you said that x should not belongs to closed interval minus 1 to 1, or should it be open interval minus?
No, it should be closed. Why? Because every time we have a strict inequality there, right? We don't want, if you put x is equals to 1 or minus 1, so either your base a or your, I mean, what is the input expression? Either this or that will become 0. So that's why we want it to be.
Ma'am, because we
Don't
want to
want to do
avoid
that.
the 1 and values 1 and minus 1. That's why.
That's why it's closed. Okay, so let's move toward activity 6.2. Is there any doubt in activity 6.2?
Ma'am, could you please just briefly explain the fifth question in this activity?
6.2?
6.1, I guess. After this question.
Okay, which question? Fifth one.
Yeah, fifth one. Like L in that one. That concept is like not clear to me.
Not getting what
Like
question.
what is the
you are
domain of the
asking.
function fx? That question. 6.1.
6.1, but question number last one, fifth one, right? What is the domain of function f(x)
Last
is
question,
it? See here what they have did, that they haven't given any base, right? So that means it's simply written to be log. So whenever it's simply written to be log, you assume that the base is 10. That's why I say that whenever you have simply log is there, simple log. So this log means it's actually log base 10. And when there is simply ln is written, then ln means log base. These are two just notations for simplifying our log. That means we don't have to write every time base 10, base 10, base e, that's one. So here, there you just have to use in question number 5. What you have to use, you have to find all the values of x for which your expression is strictly greater than 0. That's it. You have to use this fact and you will get your answer.
Yeah. Understood. Thank you.
Let's move towards 6.2.
Ma'am, the same question, ma'am. Ma'am, it's been given that the expression has negative sign in it, and we know that the negative of log is not defined.
See, but there is a much complicated expression, right? X square something. If it's no, you can't. I mean, you can't assume that way that if negative sign is there, log is negative. It's true, but when you don't have any variable there, that means if I say log of -5, then this is not defined. If I say log of -x, and if you take x to be any negative number, then what happens? Log of minus of something. That means ultimately it become positive. What I want to say. that in general, if I say log of -5, then obviously it is not different, right? But if their function says this thing that log of -x, and here if you take any x to be strictly less than 0, then what happens? Then -x will be greater than 0. So that means for all x strictly less than 0, this function is different. So that's why the domain of this function is what? If you consider this function f of x is equals to log of -x, then the domain will be this whole minus infinity to 0 open it. So that's how you have to interpret.
Ma'am, so basically we applied that rule that log of anything, let's say log of x. So we need to just check the domain of x, whether it is falling under the negative
Right.
real.
You just have to find out all those values of x for which this strictly greater than 0, this condition holds. That's it.
Okay, ma'am.
Okay, so let's move towards 6.2. So is there any doubt in 6.2?
Ma'am, in the third question, I didn't have a doubt in the question, but there was an option to find the vertical asymptote, and it's like a 3 function of log. So I solved it by the approach in the chat, but is there any like steps or formula to find like the asymptote of a log?
Yeah, sure. Let's want to say consider the function log, which of the following is true? Volume the domain log x is equals to 8 is an asymptote of. So see, whenever you have a general logarithm, you know that log base a of x, then at x is equals to 0, we have asymptotical b, right? So whenever you have log base a with something, right, then it will have asymptotical behavior at this thing will become 0. Then, for example, if you have, let's say, x minus 1, then this will behave asymptotically near x minus 1 is equals to 0. That means x is equals to. So same thing you have to do here. What we have log base 2, log base 2, log base 2 of x. So what does it means? That ultimately log base 2 of this thing
should be
whenever
0.
it will be 0, then we have asymptotical b, right? So what does it means? It means that log base 2 of x, this should become 0. But we know that log can't, I mean, it cannot be equal to 0, right? So what we will do, we will just take the expression inside the log. So what does it mean? So it means log base 2 of x, this should become 0 type of, right? So again, what we will do, again, we know that log cannot be 0. So we'll take again the inside one. So that means x becomes 0. So whenever you have x is equals to 0, then this whole log will behave asymptotically. Let us see via the graph. Is it the case? This is log base 2. It's not very difficult.
Ma'am, asymptote is the point for which y equal to 0, ma'am.
No, asymptote is the point for which actually you have that line which will
Tends to 0,
will
y
get
tends
more
to
closer and closer.
Yeah, where x tends to 0. So see, in the graph you can observe that as we the asymptotical behavior is actually y is equals to 0 line. Ultimately, it doesn't seem like that, but yeah, the asymptotical behavior happen when at near 0. it's 2. It's 2. So 0 to
It's
10.
2.
Yeah.
The x should be 2.
Answer
I have
is 2.
pasted in chat.
No, it's 2, no, because you can see the graph also.
Yeah, I pasted in chat as well. What approach I used.
You pasted in chat.
There's an image.
Yeah. Right.
Can I say something?
Yeah, sure.
The whole thing, the innermost log should be 1, so that the second, so the third log becomes asymptotic.
Asymptote.
Right.
Does it make things clear?
Right.
The innermost log should be 1.
Middle
Middle log,
innermost log should be 1 because we know that that will become 0. Yeah, right. And correct. If you want this to be 0, then I want this to be 1. That's what you guys are saying, right? Because of log base 2, 2 is equals to 1. Then again log base 2 of 1 is equals to 0. So that's why this log will have the asymptotical behavior when x is equals to 2. But the line asymptote will be y is equals to 0 only, right?
Ma'am, I'm really getting confused, ma'am. Can you just please explain it once again?
See what happened.
No, it will be x equal to 0 because you're talking, it will be an exponential function, you will be y equal to 10 to 0.
Right.
So you're confusing between exponential and logarithm.
See what happened here. We have function this function log base 2, log base 2 of x. Right. So here we have to say where the asymptote. I mean, what is the asymptote for this function, right? So asymptote will be that line which actually get parallel to the graph. I mean, as we move toward the infinity, the value, I mean, the graph should be more parallel to that. For example, if I have this graph, this is a log base a of x graph, and a, where a is between 0 to 1, then this y is equals to 0 line. Sorry, this is x is equals to 0, right? X is equals to 0 line will become asymptote, right? So in using the same concept, we have to find out the asymptote for this thing, right? So we know that when the log, whenever the inner bracket is 0, I mean the inner bracket value becomes 0, then at that point we have the asymptote, right? So what I want this log base 2 of x, this to be equals to 0. Right, and we know that the log cuts at this point, which is 1, 0. So that means if this value will become 1, then this log will become 0, and we have the asymptotical behavior there. And we know that log base 2 of x is equals to 1 when x is equals to 2. Right. So at x is equals to 0, this innermost bracket will become 1, and after this, this log base 2 of 1 will become 0, and at that point we have the asymptote. So that means this will be the graph, and this is x is equals to 2 will be this. Correct. Confused with y. Okay, yeah, right. Now it's clear?
No, ma'am. Ma'am, can you just please show it again, ma'am? Ma'am, I have some doubts, ma'am, regarding that. Ma'am, we are saying that, let's say we have been given a function log x, and we say that as x approaches 0, the graph will show asymptotic behavior. This is what we know, ma'am.
Right.
So in this function, what we are trying to do is we are trying to make log of log x tend to 0.
Right. In some kind of way, we want it to be 10 to 0, but we have to find the value of x, right?
Ma'am.
So
we find that if the value of x is 2, then log of log s will start approaching to 0.
Right. That's the thing.
Ma'am, then how are we able to conclude that the asymptotic behavior starts at x is equal to 2?
See what happens when you have simple graph of this log base x, right? So then this graph will look like this, right? So here we get intuition that at point 0, 0, and in this line x is equals to 0 is an asymptote of log, right?
Yes, ma'am. Yes, ma'am.
But we can say, but we know that log is not defined for x is equals to 0.
Yes, ma'am.
I mean, in some sense, we want this input to be
such a way that what I want this input to be equals to 0. Then only that line will become our asymptote.
Yes,
Here
ma'am.
x is equals to 0 is becoming our asymptote. So in
Yes,
this case, what happening? If you take x is equals to 2, then this input bracket is becoming 0. So that's why the 2 will be the asymptote.
Okay, got it, ma'am. Ma'am, actually, I got confused with the diagram. I thought this diagram was for log of log x.
No.
My
This
mistake,
is
ma'am.
not for
I got your point, ma'am. Thank you, ma'am.
Ma'am, can you start like open the Desmos?
Yeah, sure.
Ma'am, in that go to settings and like output values. The table one. Yeah. So it's showing so many undefined values. So are there like
Right.
5 asymptotes or so?
No. Asymptote will be only that line which will get. I mean, it seems to be touching the graph, but actually it goes along with. These lines are not asymptote because they are not. I mean, we are not seeing that kind of thing that at some point it will touches the graph. I mean, asymptote will give us a feel that at some point it will touches the graph, but it actually never does. For example, in the case e to the power x also, right? Or e to the power, not e to the power x, let's say 0.5 to the power x, right? So this graph has this kind of thing, right? So in this graph also we get some kind of intuition that this graph will touch the x-axis, right? But it's actually never does. So asymptote will be that line which will give us the feel that at much larger point it will get touch our graph or get crossed by our graph. But eventually it never happens. That line we say asymptotic behavior. Right. So I mean, all other line are too far from this thing, right? X is equals to 1 is also too far. X is equals to 0 is again far from our graph. And we are not getting that feel that it will touch the graph, right? That's why. Is it clear now? If you
Yes, ma'am.
observe this line, x is equals to 2, then you see that if you zoom it a bit, here we are getting some kind of thing that my graph is actually touching the line, right? X is equals to 2. But eventually, if you zoom much more, then you find out it never touches the graph. It seems like it touching, but it never does. It seems like the graph and the line will become, collapse, but it never does. So such type of line is going to be a
May I say something?
Ma'am, but in the recorded lectures, there is no conceptual explanation of asymptote or any such thing, and still we are getting questions regarding this.
Okay.
How are they expecting us to solve this?
I think the option
Actually,
8 only asks that is 8 the asymptote. So you can put substitute 8 and it won't come as asymptote.
but
They are not asking
right,
to
but
solve it.
still,
But still,
you
there is a
need
concern.
some.
What if there are questions that, like, there are a lot of concepts that have not been discussed in the recorded lectures, but they are in the
So, I
assignments.
mean, these are not that heavy concepts. I mean, you can just Google it out and understand, right? So that's why it given.
May I say something?
Although we assume that, yes.
It is easy. It is easy for students who are from maths background, but the students who are not from maths background, it is tough. And then we have only 2 days for the deadline.
May I say something?
No, it's hard
Yes.
for maths background also. Don't think like that.
Asymptote is not that much.
Infinity.
It's not if you are from maths background.
This time we should extend
अरे
the
सबके सब
deadline.
मत छुड़ाओ. Actually, that's not in my hand. I can say them to extend it,
You
but
started the
it's
session beginning, no, there are chances of getting. So I was very happy that deadlines are going to be extended.
For example, we can see the questions of activity 5.
Ma'am, can you take doubt from activity number 3? I have doubt in first and the last question.
okay. So this activity is over for us. See, I can't help us with the deadlines and all. Only thing I can do, I can inform that okay, students are getting difficulties to solve this graded assignment in these days.
Oh, no, it's
That's
a lot of already stats. We had multiple assignments graded. I think 4 or 5 graded assignments for statistics.
Yes, and over that we have been assigned the activity project as well for
See,
stat
that's
student.
That
Ma'am, in
always
that
happens.
asymptote question, it is like the vertical asymptote will be x equal to 2 and the horizontal asymptote would be y equals to 1. Means like it also goes to
Right.
infinite when y is there.
Right. Yeah, they have already given the line, so that makes sense. Asymptote.
Ma'am, why would we have a y asymptote over there, ma'am?
See,
Shouldn't
actually,
it
as
go
x
to
goes to
infinity, ma'am?
infinity,
Yes, ma'am.
no, this is log kind of thing. Log actually move very slowly. So when you apply 3 log together, it will become more slower. I mean,
Ma'am, but
slowly,
still
it
it will
glows very
approach
slowly.
infinity, ma'am.
No,
Means if
that's not
you
the
have
thing.
y equal to 1, it in the
No,
decimals it
wait,
looks like
sorry.
it goes to infinity.
Correct. There won't be any there
Y
won't be any
asymptote, ma'am.
horizontalism.
Yeah,
Yeah.
ma'am.
Because
Parallel to
ultimately it's
x-axis.
a graph. It seems like it have, but actually it grows very slowly. That's why
Yeah, ma'am. But it will grow, ma'am.
it will grow eventually.
Yes, ma'am.
Because the 2 is fixed there, right? Again, it will grow a bit slower, but it will grow eventually. It goes to infinity. There won't be any horizontalism.
He's right.
Okay, so let's
Can you
move toward
please
activity
repeat the
6.
questions of activity 5?
Activity 5 will go sequence wise, otherwise we missed
Activity 3, first question and last question.
First and last. Okay. So if the domain of fx is minus 3, 1, then the domain of f of ln of x is. So again, we are in some kind of composite function situation. So domain of f is already given to us. We have to find out domain of f composition G, where G is ln of x, right? So we know the rule that whenever we have to find out domain of f composition G, then what you will do? First thing, find domain of G, right? So here the function is f of ln of x, right? So we know that the domain of ln of x is actually equals to open interval 0 to, right? Now what we have to do, then we have to remove all those points for which g of x does not in the domain of f. Okay, so that means we have to remove all those points for which g of x does not belong to domain of f, and here domain of f is given to be 3 open interval minus 3 to 1. Minus 3 to 1, right? So what we have to do, we have to remove all those points for which g of x does not belong to minus 3, right? So what we can do, we can take the graph. So this is ln of x. So ln of x means log base e of x, right? So that means e is the value of e is between 2 to 3. It's greater than 0. So that's why the graph will look like this. It's the graph of ln. Now, what we want to find all those values of x for which my ln of x lies in this interval minus 3 to 1, right? So this is minus 3, suppose, and this is. So what we have to do, we have to remove all those x for which the graph is coming into this interval, right? So if you observe this point is 1. So if the y value is 1, then what will be the x value? So what I want ln of x to be 1. So ln of x is equals to 1. So that means that log base e of x is equals to 1. That means e to the power 1 is equals to x. That means x is equals to 2. So this point is e comma 1, and similarly you can observe this point is e to the power minus 3 comma minus 3. Right. So what I want to remove all those points for which this thing will. So that means I have to remove e to the power minus 3 to 1. Right. Remove this bracket e to the power minus 3 comma 1 comma e from 0 to infinity. Then that will be your domain. So what's the answer given to us?
It is the inverse.
Find the domain of this.
This is the region only where this is valid.
This is very different. Why is this so?
Why we have to remove it?
We have to remove all those points for which ln of x does not go. Sorry, I did it wrong. We have to take all those points for which, yeah, correct. I mean, we have to find the domain of f composition G. So find the domain of f, which is 0 to infinity. Then we have to remove all those points for which it does not belong to domain. But if you take any point between this interval, that e to the power minus 3 any, you will, I want to say that if x belongs to e to the power minus 3 comma e, then you can easily imply that your ln of x will belong to minus 3 comma 1, right? And this is the domain of it. Otherwise, if x does not belong to in this interval e to the power minus 3 n, then this will imply ln of x does not belongs to minus 3 comma. So that's why we have to take all those points for which ln of x belongs to the domain. So that's why the answer is e to the power minus 3. Is it clear? Or I confused?
Yes, it is.
Ma'am, can you just please go scroll a bit up, ma'am?
Yes.
Ma'am, we got x is equal to e. Then after that, what you did, ma'am? I just got confused, ma'am.
Again, we did the same thing. See, what I want to find that value of x for which the value of ln x is equals to minus. That means I want ln of x to be minus. That means I want log base e of x to be minus. Again, we use our...
Ma'am, why are we saying that ln of x should be minus 3?
See, what we have to do, we have to remove all those points for which gx does not belong to domain of f. Domain of f is given to be minus 3 comma 1. So what I want to say, I want to find out those values of x for which my graph ln of x takes value between this line. Then only f of ln of x makes sense, right? If ln of x does not belong to this interval minus 3 comma 1, then f won't accept that to be its input, right? Only f will only f will work when my ln of x belongs to this interval minus 3 to 1. That's why I try to find out, because ln of x graph look very simple. If you find out the value of x where it gets value 3 minus 3, and if you find out the value of x where it gets the value 1, then all other points actually lie between them. I mean, all other points will...
We are trying to say over here is the interval e raised to minus 3 to sorry.
So it seems like a composite because we fx. So we had a fx and we are trying to find log of fx, right?
Huh.
If you can say that.
Ma'am, this graph is a generic graph, right? You didn't.
It's a graph of ln of x, right?
Yeah, but it is a general graph of ln of x, right?
Huh.
We don't have to do anything special to plot the graph.
No. But yeah, but how you will find out the values of x, right? Ultimately, scaling doesn't matter. The concept matter. Why I draw the graph? Because if you find these two endpoints, then all other points lie in between them. That means the whole interval makes sense, right? That's why we need that graph. Otherwise, otherwise, how can we say that all points does not lie between them? For example, if you have such kind of graph, then if you take 2 points, suppose this, and suppose, okay, don't think about this. You guys, I mean, get the question, how we want to solve such type of domain question.
Yes.
Right?
Yes. Can you solve the last one also?
Can I give a suggestion?
Yes.
Please draw 2 graphs. One graph for the final output.
But f is not known to us, so how can we graph?
The domain on which it is valid will be marked. Then the other one which generates the domain. Then we will know the x range which is valid.
Yeah, that's a you can say.
For the kids, you please draw 2 different graphs. Tell them this is the input for which the final graph is valid.
Okay.
To generate that input, the other graph should be in this range. Then they will understand.
Excuse me.
Yes.
Bhaskaran sir, how can I get in touch if I want to?
You can contact dad@markshe.in.
Give me a second. Let me type it.
DAD, dad@markshe, MAKSHI.in.
.in. Thanks a lot.
See, this question is not that much difficult. I mean, you can, all things are in 2 to the power x type of thing. First thing, you apply ln on both sides. I'm talking about the fourth question.
I tried, but it's not, I'm not getting the answer.
Okay, so it says that we have to solve for x of e to the power 2 to the power x minus 2 to the power x. And this minus 12 is equals to. So what we will do? So we'll again use our identity. So what does identity says? That you can either apply ln on both sides, and or you can just use this thing. Y is equals to x, you can move left. Y is equals to log base of x, right? So here, just compare the variables, and you will get 4 to the power x minus 2 to the power x minus 12 is actually equals to log base a is there, so that means it will become log base e. So again, it will become ln of, and ln of x is there. So in place of x, we have 1. So ln of, again, we know ln of 1 is 0. And this thing
0.
that 4 to the power x is there. So in place of 4 to the power x, what you can do? 2 to the power 2 to the power x, right? So that all things will come into 2 to the power 3. So it will become 2 to the power 2x minus 2 to the power x is equals to 2. Again, what you can do? Apply both sides log base 2. So if you apply both sides log base 2, what you will get? Log base 2, 2 to the power 2x, and here we have minus of 2 to what? So okay, so let's common first. So what we can do? We can take 2 to the power x common, and other things will stay as it is. So what will be here? If we take 2 to the power x,
Ma'am, 2 to the power 2 minus
2 to
1.
the power x still will become, no? I mean, I want to, but it's okay. That's okay.
There is 2.
Now apply log base 2.
Ma'am, how can we separate?
It will be
2 to the power 2, ma'am.
right?
There is not
In the
x.
bracket. You
In
took 2
bracket.
to the power x common, so you will have 2 to the power 2 minus 1.
Yeah,
Ma'am,
2
even
to the
power
power
No,
2
no,
minus
no,
1.
no,
added,
no.
ma'am. I
Wait.
think
If you multiply them, then it will be 2 to the power x into 2 to the power x, which is 2 to the power 2x, right? And 2 to the power 2x is 4 to the power x. Is it correct now?
Just a minute.
Yeah.
Substitute y equal to 2 power x, you will find a quadratic, solve that, and then reverse it.
That's also fine. Yeah, that's also correct. What you want to say, that will be a move generator. This is also fine. After, if you do that, simply take y is equals to log base. No, y is equals to 2 to the power x, right? And then you will get a quadratic equation here, and you can solve it, right? We have
stuck with the log 12. This is the
right.
Yeah, but ma'am, please do convey the message that week 5 is tough even for instructors as well.
No, it's not tough actually. It's actually
No,
we
but
haven't done.
For us it is. For us it is.
Think beyond. That is
See, if we, I mean, if you, what's the point if you can't get some challenges there, right? Only you can learn if you find tough thing. Otherwise, there is no point.
Look,
see,
Ma'am,
I
the
told you
problem
these
is-
are
the
very
problem is
basic
time.
mathematics.
You know, 2 power
Okay,
2x.
there always a time constraint.
Wait a minute. 2 power 2x and 2 power x. It's glaring that somebody is twice the other, right?
Right.
So it suggests you it should be somewhere square minus itself. So y square minus y equal to 12. Y becomes either 6 or 5.
Yeah, there are pretty much. I mean, you get the question. I mean, how to solve it. There's a one very, I mean, this is a very famous way, converting into polynomials. Not this question. There are so many questions which are actually based on this way, converting into polynomial. What does it mean? So it means you will find out some common factor, replace it by some other thing, and you will get either a quadratic or a cubic polynomial. And you know how to find out the roots of cubic or quadratic polynomial. In many cases, it will be a quadratic polynomial. After that, you will get the answer. Okay. Is that fine?
Actually, you try to solve
Yes, thank you.
putting 2 power x as y, then we get answer as 4. 4 and minus 3.
You are right.
Okay. 4 and minus 3.
Yeah,
the answer is 2.
ma'am.
But the answer is 2.
So what we get 4 to the power x.
4 is 2 power x. So x is 2.
Yeah, correct.
Hello. Yeah, so if you take y is equals to 2 to the power x, then what happened? You can write this it to 2 to the power x to the power, right? Minus 2 to the power x minus 12 is equals to 6. So that means it will become y square minus y minus 12 is equals to 6. Oh, okay. So that means y minus 3 and y minus 4. Y minus 4, y plus. So see, here the main concept comes.
Ma'am, it
That
should be
means,
positive then.
Y can be only
see, I want minus. So y is equals to minus 3 and what have become y is equals to. That means what does it means? That 2 to the power x is equals to minus 3 and 2 to the power x is equals to.
Greater
But
than
you guys
0.
know that exponential can't take a negative value. So that's why this case will get discarded. And we remain with this thing. And the answer is x.
That's correct.
Okay.
So that means from here to here, you have to think about that which value will get discarded. I mean, it's actually not that tough because exponential function can't take negative values. So you can use it. So can we discuss other questions into other session? That will be fine for you. Otherwise, we can solve one two attempted questions. See, logarithmic actually calculation will be there, but the main thing is you have to understand the concept. How does log comes? How does it define and why does it define? Other things, I mean, questions obviously, if you practice it, you will get more fluent, but just understand the concept. This is very famous way to solve such type of question, the converting into polynomials. Okay, keep in mind. Mainly major logarithmic or exponential question will get solved by this method, converting into polynomial. Here you will have to convert into some polynomial, you will get some cases, discard some cases, and you'll get logs. So is that fine if we discuss other questions into next session, because next session is on tomorrow itself?
Ma'am, I have one question. Last question.
Ma'am, when will be the next session?
Tomorrow, I think. In your calendar, it's scheduled on tomorrow, right? Tomorrow you have a session. Open session for motion.
Can I ask a question, ma'am, or a last question?
Right. Ask.
Ma'am, log of x minus 1 base 8 plus log of x plus 1 base 8 is equal to 1. Okay, while solving
what?
log of x minus 1 base 8 base 8
minus 1 base 8
plus log of x plus 1 base 8 is equal to 1. So solve for x.
Is this this does not belong to graded assignment, right?
This is not belong to this only one of the solved questions by professor in section 5.6.7. So I have doubt in that. Okay, in that x square minus 1 is equal to 8, correct, ma'am? X square is equal to 9 is coming. When you solve, x is equal to plus or minus 3 is coming, correct?
Oh, wait, what is your doubt?
Yeah, let me come to doubt. Ma'am, we are listening. X square is equal to.
Just give me a second. I will see the
I will
schedule.
explain. I will listen to me. Both the bases are same.
Yeah, finally, x square is equal to. We are landing
Both
at
the
x
bases
square is
are
equal to
same.
9.
The formula or the logic is we know log A plus log.
Sir, listen, please. Finally, we are landing at x square is equal to 9. Correct, ma'am?
See, what you are getting, x square minus 1 is equals to 8. So that means.
Yeah. So we are landing at x is equal to plus or minus 3.
Correct.
But the professor
So x is equals to plus or minus.
Professor
X is equals to
only
minus 3.
or plus
We
3.
discarded because the domain of logarithm is 0 to.
Why, ma'am? When you see only function of x log of x square minus 1, we can accept minus 3 also, correct? When you split into as per logarithmic properties, why you can.
But see, here it's given x minus 1, right?
Yeah.
X minus 1 is there. But if you put x is equals to minus 3, you will get minus.
Yeah, but if you
So
see
minus 4,
the whole
this log is
function,
not.
when you see as a whole function x log of x square minus 1, it is acceptable, correct?
No.
Domain is not accepted.
Log of x square minus 1 is there, right?
Because log of x square minus 1 is nothing but log of x minus 1 plus log of x plus 1. So both are similar as per, both are equal as per logarithmic properties. So when we are acceptable in one form, why not is acceptable in other form?
See, it is not given here that this is your function. It is given here that this is your function. These two functions, these two expressions. No. That's not equal. They both expressions are equal, but that's the main thing now. These two expressions are equal. That I know that x plus 1 base 8 plus log base 8 of x minus 1. This is same as log base 8 of x square minus 1, right? These two expressions are equal. But when I say that my fx is this this expression log base 8 x plus 1 plus this thing, and if I say that my another function is this function log base 8 of x square, now as a function they are not equal because as a function they have different domain.
Okay.
Different set of values are acceptable in both of them, right? Here you are accepting all the values which does not belongs to closed interval minus 1, right? Okay. If you take any values beyond this interval, that will be acceptable. But this function f, he won't accept. He said that x is equals to minus 3, he can't able to find out anything. So as a function, they are different. So that's the thing we discarded minus. So your doubt is nice, I mean good, but you have to think as a function also.
Yes, it is given. Okay.
That's the one. That's why we are getting two different things for domain also. When I say that when you have to find the domain of f composite G, don't go via expression because expression leads us a bit mistake. I mean, you will either leave some points or take some extra points in your domain. But when you go via steps, that will be. So same thing is happening here. There are as a function, they are not same, but as an expression, there's.
Okay, thank you.
Is there any other doubt?
Can I say something on this?
Yes.
If f of x is equal to g of x, they are equal where both are defined. So the left-hand side domain can be different from the right-hand side domain. That is exactly yes.
Yeah, right. The domain is not that's why.
I think that he is confused. Why is the domain not the same? Domain will not be the same. F of x is defined in some region. G of x is defined in some region. They may be same in some region. This is the difference where you have got to figure out.
Yeah, right. See, another thing.
The range would be given that for this particular thing, both are same.
Domain.
The range will be same because the expression is right.
Don't get
so
confused.
Whatever.
It's getting confused in domain and range.
I'm saying the range of values. I'm not saying about the range of a function. I'm just saying that for the range of the values, those functions has to come.
Domain is the place where it is defined.
Correct.
It is the output. We are not talking about output may the same.
I am not saying about the output, sir. What I'm trying to say is when we say two functions are equivalent, we don't say that their domain have to be same.
No.
But
no. That's not the thing.
No, when we say something are equal, we do not say In this case, at least we did not say it is same throughout the region.
Right. So the whole the number of points are defined to be different.
Listen to
That's
this.
why.
If log of x plus 1 and log of x minus 1 has been defined in some region, we came with log x square minus 1 by multiplying, but we did not define where it is valid. So the domain, we left it. That is why it will be different. It is equal to log x square minus 1 only where log x plus 1 and log x minus 1 are defined. So that is a place where you got to concentrate. Log x plus 1 is not defined for minus 3.
So that's why we discard minus
3. We should not go by the log x square minus 1 because we came with that concept. We used some property and multiplied, and that gives you an illusion that it probably should be valid for minus 3, which is wrong.
Okay, so is there any other doubt, or we can
Ma'am, so
wind up
in this
our
case,
session
what
here?
are we saying when we say equality of two functions? Are we not
See,
matching the domains?
equality of two function actually depends on so many things. First thing, your function should define on both should have the same domain terms. Then only we can compare them. If your equality of function is actually very big thing to say, because in that case you want domain to be same, you want your range set to be exactly same. Why exactly same? For example, if I draw two functions, for simplicity, let's say this is my one function and this is my another function. It's actually exactly same at over these points, but it will be different. Suppose now I state two statements that this is my g and this is my. I'll say f and g are entirely same. F and g are equal over. You have to give some region. Over that region, only we can say two functions are equal. For example, this is my 2 to 5 region. Over close interval 2 to 5, they are equal. But otherwise, if I say over, let's say 0 to 7, then they are not equal, right? So that means equality of function is actually depending on the region also. At what region you want to say they are equal. Here, we discard x is equals to minus 3 because we start with log of 1 minus x. If we start with log of x square minus 1 and then do all the calculations, then the minus 3 will get some place. But if we start with log of 1 minus x, then that's not the case. We can substitute x is equals to minus 3. Is that clear now?
Yes, ma'am.
Good explanation.
Fine. So if there are no other doubts, we can wind our session here. Do you guys want the PDF?
Yes, ma'am.
So how many courses do you guys have? 3?
Ma'am, activity 5 questions.
Activity 5. We can discuss in later section if possible.
It contains only 2 questions, but as you are comfortable, you can proceed.
Okay, so activity 5 or week 5?
No, activity 5 of week 6.
So we'll continue these questions into next session, right? Because there will be a purely dedicated session for doubt solving and practice. So you can ask there.
All right, ma'am.
Just wait a second. I'll share the PDF in the chat. So is there any feedback for class? You can give it to me. Yeah, I've shared the PDF. You guys can leave it. You want to discuss anything else? You can stay, otherwise I also leave within 10 minutes.